Computational fluid dynamics, CFD, is a branch of fluid mechanics, and a computer-based tool for simulating the behavior of systems involving fluid flow, heat transfer, and other related physical processes. It works by solving the equations of fluid flow in a special form over a region of interest, with specified, known, conditions on the boundary of that region. To perform CFD analysis, in ANSYS we have two codes, one is Fluent and other is CFX. ANSYS CFX is a high-performance computational fluid dynamics CFD software tool that delivers reliable and accurate solutions quickly and robustly across a wide range of CFD and multi-physics applications. CFX is recognized for its outstanding accuracy, robustness and speed with rotating machinery such as pumps, fans, compressors, and gas and hydraulic turbines. We know that the pumps and compressors are common components. An estimate of the pumping requirement can be calculated based on the height difference between source and destination, and head loss. Estimates for the pipe and any obstructions, valves along the way. So, investigating the detailed flow pattern around the valve, however, can lead to a better understanding of why these losses occur. Improvements in valve design can be simulated using CFD, and implemented to reduce pumping requirements and costs. In our example, we are considering a butterfly valve in the pipe structure to examine the behavior of fluid across the valve. A butterfly valve is a valve which can be used for isolating or regulating flow. The closing mechanism takes the form of a disc. Butterfly valves are commonly used in industrial applications to control the internal flow of both compressible and incompressible fluids. A butterfly valve typically consists of a metal disc formed around a central shaft, which acts as its axis of rotation. As the valve's opening angle, theta, is increased from 0 degrees, which is fully closed condition, to 90 degrees, which is fully opened condition, fluid is able to more readily flow past the valve. And the fluid flows can contain particulates that affect the flow and cause erosion to pipe and valve components. We can consider the particles' presence in flow. The particle tracking capability of CFX is useful to simulate these effects. This video demonstrates the fluid flow or CFD analysis using ANSYS CFX code. As mentioned before, the example considered over here is the model of butterfly valve in a pipe. The analysis type considered is steady state, with general fluid and flow in a single domain. The turbulence model used for the analysis is K-epsilon model. The K-epsilon turbulence model is the most common model used in computational fluid dynamics to simulate mean flow characteristics for turbulent flow conditions. It is a two-equation model, which gives a general description of turbulence by means of two transport equations. The original impetus for the K-epsilon model was to improve the mixing length model, as well as to find an alternative to algebraically prescribing turbulent length scales in moderate to high complexity flows. The fluid material for the flow analysis used is water, which flows at certain rate of velocity through a pipe of diameter d that has a rough internal surface. The velocity profile is assumed to be fully developed at the pipe inlet. The flow, which is controlled by a butterfly valve, set to an angle of theta, to the vertical axis, and considering the flow contains some sand particles, of size range in microns, having a particular value of equivalent sand grain roughness, using a rough wall boundary to simulate the pipe wall and CFX pre. The analysis procedure for this problem involves importing the geometry from the CAD modeling software. Next, performing the Boolean operation to remove the volume of valve and pipe body. Then the model material is assigned as Fluid and Design Modeler, and we need to create a symmetry to reduce the computation time. Afterwards, the named selection will be done to define in which direction the flow is taking place, means need to mention the beginning and ending process of flow, that is the inlet and outlet phases, and also to define the symmetric phase. Next comes the mesh generation. For the model and the analysis, we used curvature and proximity mesh controls to get fine mesh at the curve's end. Small gaps near the valve region. And inflation is used on the pipe wall and the faces of valves, and mesh is generated. Then the mesh model is taken for CFX analysis. In the setup, we have to define the sand particle material and fluid material. After defining materials for analysis, we have to define boundary conditions. For inlet, we have to create a fully developed inlet velocity profile using the CFX expression language. A fully developed fluid flow through a pipe is one in which the boundary layer extends to the center line. Hence the maximum velocity of the boundary layer is the same as the center line velocity of the pipe. As fluid enters any pipe or channel, boundary layers keep on growing till they meet, after some distance downstream from the entrance region. After this distance, velocity profile doesn't change, flow is said to be fully developed. Here we consider fully developed velocity profiles, with respect to accuracy point of view. Then we getting into setting up a particle tracking simulation in CFX to trace sand particles. Afterwards, we need to consider initial settings for the problem and setting of solver controls before defining the run. And finally, animating particle tracks in CFX to trace sand particles through the domain after solution is done. In the video, you can see the animation on the left-hand side. The colored line which are seen throughout the length of pipe or domain are called as steam lines, and the spherical balls which are running along the steam lines are called fluid particles. At the inlet you can see fully developed velocity profile, and also we can observe the velocity distribution and the behavior of the fluid across the butterfly valve in the pipe structure. And we can also measure the maximum, minimum and average value of pressure at the outlet by using function calculator. An important consideration in this simulation is erosion to the pipe wall and valve due to the sand particles. A good indication of erosion is given by the erosion rate density parameter, which corresponds to pressure and shear stress due to the flow. On the right-hand side, you can see the plot of erosion on the valve surface and side walls due to the presence of sand particles in the flow. As can be seen, the highest values occur on the edges of the valve where most particles strike. Thank you for watching the video. For any queries, projects and training sessions, you can contact Key Worldwide.